Every once in a while, it's good in the course of a program to go back and do a quick review of something we've covered before. Now that we have a lot of new topics under our belt, let's go revisit the refrigeration cycle in this quick PowerPoint, and let's take a look at some of what we've learned and why it affects the refrigeration cycle and why it's so important. Okay, so we have to go back and remember that we have the main components of the refrigeration cycle. Okay, it has four main components. It's in every refrigeration system and it will not work without any of these. We have the compressor. It's considered the heart of the system. Remember, it's a vapor pump. The other thing to remember is that it cannot pump liquid without damaging the internal component. Liquid refrigerants do not compress, okay? So it acts like hydraulics. If you try to compress fluid, it's going to exert outward pressure on parts and components, and they're not built for that. The other thing we have to remember is the refrigerant flow through the compressor is what cools the compressor itself. Okay, the oil in the compressor components are all cooled by that flow of refrigerant gas through the system. So that's why it's very important we never run the compressor when there's no refrigerant. The condenser does three things: it desuperheats, it condenses, and it subcools. Okay, it is always larger than the evaporator. The condenser always has more surface area and more internal capacity than the evaporator. It can be air or water cooled. Now, that surface area might be in multiple passes of a coil. So just be aware that if you see a condenser coil that's only 12 by 12 or 12 by 24, look how thick it is. Okay? If it's air cooled, the air is being pulled through it towards the compressor. Okay? You never want to be blowing air the wrong direction in the condenser coil. It's always being pulled through. The metering device, it actually causes the pressure lowering of the refrigerant as it enters the evaporator. When the pressure is lowered, the boiling point drops. Okay, and again, we're referencing Charles' law of ideal gases. The temperature and the pressure are directly proportional. When one increases, the other increases, and vice versa. Okay, so what we're doing is in the metering device, we're doing a quick pressure drop. We're dropping from a high pressure to a low pressure, maybe going from 200 psi down to 60 psi. At that point, the temperature of the gas and the boiling point drops significantly. The evaporator is where the heat absorbs. It lowers the sensible heat of the air and removes the latent heat of the water vapor, humidity that's in the air. Okay, the evaporator basically boils off the refrigerant inside of it, the liquid refrigerant, by absorbing the heat. Okay, because it requires heat to make any liquid boil. And then the gas, or the equivalent of the steam, if you're talking water, which we're not in this case, goes back to the compressor. Okay, so we boil off the refrigerant in the evaporator by using the heat of the space surrounding the tubes. And because we wanted a really cold environment, that's why we have to lower the pressure with the metering device to cause that low pressure, low temperature environment. Okay, to quickly identify if the liquid line is full of liquid to feed the metering device, some systems have a sight glass. Now, these are not the primary components anymore. We've already covered the four primary components. These are all additional possible components. The sight glass. The most important part of the sight glass, if it exists, is to see is the moisture meter that's on it. Okay, more and more systems are not including sight glasses because you cannot properly use them to charge a system. The filter dryer, you'll find it in most systems, but it doesn't have to be there. The filter dryer traps particulate matter and moisture in the refrigerant. The moisture is absorbed by a decadent and held there to slow the formation of acids. So again, the filter dryer is not there in every system, but it's worth mentioning because quite honestly, anytime you install a refrigeration system or change a component out that causes you to open it, you should really change out that filter dryer. There are three refrigerant lines that you'll find in most every system. You have a discharge line that runs from the compressor to the inlet of the condenser. This one is really hot. You have the liquid line from the outlet of the condenser to the inlet of the metering device. Okay, this should be about body temperature. If you grab hold of this with your hand, you shouldn't burn yourself. It should feel roughly around your hand temperature. Suction line from the outlet of the evaporator to the inlet of the compressor. This is always gas. You should always have vapor refrigerant in this, and it's going to feel cold to the touch. Okay, sometimes in a freezer, in a low temperature freezer, it's going to have ice on it because it's very possible it's under freezing. Now, what we're going to do is we're going to go through the different states of the refrigerants. Okay, high pressure, high temperature, low pressure, low temperature, superheated vapor, and subcooled liquid. Okay, so beginning with the discharge line. Okay, in the discharge line, we have a high pressure, high temperature, superheated vapor. All we mean by superheated is that it is far above the condensing point or the evaporation point. Okay, so we have 2 points here. We have a evaporation or boiling point in the evaporator, and we have a condensing point in the condenser. All superheated means it's a vapor and it has a higher, much higher sensible heat than the condensing point or the boiling point. Then we move out of the condenser into the liquid line. I have a high pressure, high temperature, subcooled liquid. Again, all we mean by subcooled liquid is the temperature, the sensible heat of the liquid in this line before it gets to the TXV is below the condensing point of the system. Okay, so let's say my condensing point is 30 to 35 degrees above the ambient temperature around it, which is typical for refrigeration. My liquid line is subcooled, and it's going to be under that condensing point. We've removed more sensible heat, and that's normal. You want that. Okay, then we move through our evaporator, boil off the liquid refrigerant. I now have gas. Okay, coming out of the evaporator, we have my suction line. Suction line is going to be a low pressure, low temperature, superheated vapor. In other words, it has gained sensible heat over the boiling point in the evaporator. We have 2 points of pressure change in the system. We have my metering device, changes from a high pressure to a low pressure, and we have my compressor, changes from the low pressure to a high pressure. Okay, metering device takes that liquid, the solid liquid column in the liquid line, and sprays it like out of the end of a garden hose into the evaporator, and therefore causes the pressure drop. Okay, subcooling occurs in the last half of the condenser. Subcooling is the temperature of a liquid below its saturation point or condensing temperature. Okay, saturation and condensing is the same terms basically. The higher the subcooling number, the more heat the system will absorb. Superheating occurs in the last half of the evaporator. The evaporator superheat is the temperature of vapor above its saturation or boiling point. So again, above the point it changes from a liquid to a vapor, we add sensible heat. If our superheat is too low, the more danger we have of getting liquid refrigerant back to the valves of the compressor. You want to have a superheat of 8 to 12 degrees. Now, let's think about this when we talk about defrost, as we've been talking about. If my temperatures are too low or my pressures are too low, I will not have as the pressure drops, the temperature drops. So the closer the temperature is to the space around, the less heat I'm going to absorb. So we got to be careful to make sure we absorb enough heat to get our liquid boiled off before it gets back to the compressor. Flash gas occurs with the pressure drop at the outlet of the metering device. It helps lower the temperature of the refrigerant. Again, lower pressure, lower temperature. Back to the gas laws. By the second law of thermodynamics, energy flows to where there is no energy, in other words, colder environment, from the hotter environment. Okay, this is why the evaporator absorbs the heat from the air passing through it. So as long as my evaporator pressures and temperatures are always lower than the space around it, okay, we're going to absorb heat. But we have to have enough of a difference so that we don't pull liquid back to the evaporator. We always have to absorb enough heat so we don't pull liquid out of the evaporator to the compressor. Again, it's also why the temperature of the refrigerant must be greater than the ambient air passing through the condenser. We have to have our temperature of our gas coming into the condenser higher than the ambient air around it or the atmosphere around it. Okay, rule of thumb, 30 to 35 degrees above the temperature of the air around it. So that's a very quick check if a system's charged properly or not. 30 to 35 degrees above the air around it. We need to maintain a compression ratio of at least 3.5 to 1 and not more than 10 to 1. And again, this is not something you need to measure. Okay, this is something you're going to see on your specs for your compressors for your entire systems, okay? But a 3.5 to 1 and not more than a 10 to 1. And that probably comes up on some of the certification and licensing exams. We also have to worry about the quality of the refrigerants, okay? For a refrigerant to be used in our industry, we have to worry about three main guidelines. One, it has to be stable. It cannot break down. It must last and go through change of state hundreds of millions, if not billions of times in its lifetime. We do not want refrigerants that can be used up or destroyed in a system that is operating properly. It cannot lose its molecular structure nor change its chemical makeup on its own. You hear customers on occasion tell you that a prior technician or a prior company said they have to change out the refrigerant on a system. This is not accurate. You should never have to change the refrigerant on a system unless there's a breakdown of the compressor oil and the compressor windings, okay, which will cause acid. Then you have to recover and recharge and clean the system out. You cannot have flammable refrigerants. Now, I'm going to talk more about a slight change to this, but refrigerants are supposed to be non-flammable. Its flammability must be low to non-existent due to the fact that it's under pressure and we could become a ticking time bomb in the presence of fire. It could create an explosion possibility if the unit was leaking into an enclosed structure, just like natural gas or propanes. Now, we're talking 2016, 2017 here. We need to be careful on this because there are some newer systems coming out that actually use propane to cool as a refrigerant. So just be aware, and just as a little side note on here, if you ever see a system that has propane as a refrigerant, you cannot use the identical tools you use with other refrigerants, and you got to be very, very careful and get some special training. Refrigerants have to be non-toxic, okay? While it's still dangerous from its ability to displace oxygen and become an asphyxiate, it has to be non-toxic. Okay, in other words, you cannot have lingering health effects that increase over time with exposure to refrigerants. Again, you don't want to breathe it in because it will drown you because it displaces oxygen, but it cannot have toxicity. For refrigerants to work as efficiently as possible, they need to have a low heat of evaporation or boiling point. The further apart the temperatures are, the faster the heat transfers and the more efficient a unit will be. So in other words, if I have a freezer and if I'm running my evaporator at 20 degrees and I want to have a box temperature of 0 degrees, my difference between my evaporator temp and my box temp is 20 degrees. Okay, if I have a 10 degree or negative 10 degree evaporator and a 0 degree box, it's only 10 degrees difference. So my better idea is to have a negative 20 degree evaporator for a 0 degrees box because I have a bigger difference between the two temperatures. Now this is a little bit different on air conditioning, okay, and on some units where we want to maintain humidity. The further apart the temperatures are, the more humidity I'm going to remove from the air. So if you're dealing with a flower cooler in a grocery store or floral shop, you don't want to pull the humidity out or someone's going to be getting dried out flowers. So what you do is you keep the evaporator temperature very close to the box temperature. So if I will have a 45-degree box temperature, my evaporator temperature may only be 40 degrees because I want to keep as close as possible but still be able to maintain my cool temperatures. So again, this is just a replay of everything we've gone over here. We have our compressor and our metering device. That's my point of pressure change. To the left is my low side. To the right is my high side. We have the condenser that rejects heat to the outside because the boiling points and the condensing temperatures are over the outside temperature by about 30 to 35 degrees. We have my evaporator on the left side here, which absorbs heat because it is below the space temperature by about 20 degrees. So heat is going to migrate into the evaporator and cause the refrigerant to boil off. We have my suction line, which is a superheated vapor. We want about 8 to 12 degrees of superheat. We have my liquid line, which is a subcooled liquid. We want about, sometimes usually 10 degrees, 8 to 10 degrees of subcooling, but this varies with the condenser design. So just always look up the factory on subcooling. Metering device changes the high pressure liquid to low pressure flash gas. And my condenser desuperheats, condenses, and subcools. My evaporator boils and superheats. Okay, so this diagram here is one you really want to know. If you have anything you want to study, this diagram is the one I suggest you spend a few minutes with.